Hi everybody, this is Mr. Folly, and welcome to part 3, where we're going to look at graphs and graphs and graphs and graphs and graphs. So what we're going to do first is just show you basically what the graphs look like. So I have a rate equals k a to the 0, okay? So if I'm looking at this a to the 0, that means that it has to be present, but concentration doesn't matter. Okay, so remember it's going to be a sub t equals negative kt plus a naught. Okay, concentration of a naught. So this will give you this is time, and this is concentration of a, and it is just a straight line, and that's it. That's not so bad. But if it's first order, again, we're looking at y equals mx plus b, and notice how we're changing these. This is now lna, right? This is still time. And y equals mx plus b. Notice it's going to have a negative k, so it's going to have a negative slope, okay? So first order again, so this would be rate equals ka. Now, these graphs will only ever do only one at a time. So you can't change the concentration of B. You won't have like two lines on it. So there won't be like another one that would be like B or something like that. So just one at a time, okay? Second order reaction, pretty much the same thing, but notice K is positive. Well, K is positive, and the slope is positive, okay? So that's kind of the deal on that one. And this one's going to be 1 over A, and this is going to be time. Okay, and this would look like rate equals K A squared. Okay. All right, so we can also find half-lives, and we see these, and do these get kind of ugly quick. Okay, so I'm going to focus on them one at a time. So if I'm looking here, your sheet has better resolution than mine does. Notice how this is 5, right? And this is just the concentration of, let's say it's A, okay? So notice the concentration is A. Here's 2.5. Boom. Notice this is your half-life, okay? So this looks like it's 1, 2, 3, 4. So this is 2. So this is 20,000. So this right here is 10,000. So notice how it is constant, right? Concentration of X. So this is 0 order. And this, we're looking at a 0 order. So half-life is constant. Okay. 0 order. If you have more initially, the half-life is longer. Okay. So, oops, I think I looked the wrong one. Yeah, I looked at the wrong one. So half-life is constant on that line, okay? So nuclear reactions have a half-life of T1/2 equals ln2 over K, because nuclear reactions are always first order. No tricks, no exceptions, it's constant. A shorter half-life means a larger K. So these are things algebraically you can play around with, but it's really good to know, okay? If it's 0 order, if you have more initially, okay? If you have more initially, the half-life is longer, okay? Algebraically, see below, and we'll look at these in a second. First order, again, half-life is constant. Second order, if you have more initially, the half-life is shorter. So we'll play with that in math here right about now, okay? So another table that does that, the differential rate law. Rate equals blah, blah, blah for 0. Notice how concentration versus time, it will go down to 0, right? Integrated rate law, another way to do it, A equals A naught, negative KT. Straight line plot of concentration versus time, slope is negative K. First order, if I graph concentration versus time, notice that's curved. Second order, concentration versus time, notice that's curved, okay? Then when I change my y-axis and make it ln x, that would be linear, okay? And if it is second order, I'd have to do 1 over A, and that's going to get you to linear, okay? So hopefully that you can see how that works. So again, this is molarity versus time, and then these are linearized is what that's called. And if you remember that from physics, I think you linearize things a lot. Relative rate versus concentration. So notice for zero order, again, just put this down here, we have 0, 1, 2. So if my concentration is high, notice my rate is constant. If my concentration is high, my rate is high. If my concentration is high, my rate is on. My dog is digging. And then the half-life, so we can get that through now. Units of K, again, we can figure that out with algebra like we did before. So that's it. So, quick things to remember. For rate laws, exponents are not coefficients. They must be determined by experiment. You can use the formation of a product or loss of a reactant to determine rate. Only concentrations are used. And that, my friends, is it. And I will say, toodles.